All right, applied calculators. In this screencast, we take a look at the derivatives of exponential functions, which is something that should be straightforward for us, right? We know that the exponential function looks like this. It's smooth all the way through, and so we're supposed to be able to draw a tangent line, draw a tangent line, draw a tangent line, right? Everywhere we're supposed to be able to draw a tangent line, and if we're supposed to be able to draw a tangent line everywhere, then we can find a derivative. And so there's a theorem that says that if y is e to the x, then its derivative is also e to the x. And this isn't really very bad to prove. Let's prove it. We're going to take the limit as h approaches 0, right? This is that 4-step process where we figure out what our function is at x plus h, and we figure out what our function is if it's just x, and we divide by h. And so in this case, the function is e to the x, but if you replace that x with an x plus h, you get e to the x plus h. And then we do a little bit of algebra. We remove an e to the x, and what's left is an e to the h minus a 1 over h. And so the whole proof boils down to what that is. The whole proof boils down to, as h gets closer and closer to 0, what happens to this? And so let's pull a calculator up. Let's figure out what e to the, let's do this correctly. E to the 0.1 minus, all right, because what was it? It's e to the h minus 1 over h. That's 1.05. And what if we get that closer and closer to 0? That's really good. And then what if we try to get even closer to 0? That's really close to 1. And so what we see is that as h gets closer and closer to 0, this gets closer and closer to 1. And so the derivative of e to the x is e to the x. And that's what that says. That's what that says. The derivative of e to the x is e to the x. Once you know this, once the derivative of e to the x is e to the x, then we can find all sorts of derivatives. We can find all sorts of derivatives. Let's do the derivative of e to the x squared, and then let's do the derivative of e to the x over x squared plus 1, and then let's do the derivative of x squared times e to the x. Let's do that just to make sure we know all of the things. You may want to hit the pause button and see if you can do those now. Okay, so let's give it a go. This is e to the chicken nugget, so its derivative, you take the chicken nugget, right? That's how that goes. And you multiply by the derivative of chicken nugget, right? Like that's it, right? That's that thing there. And then we see that if we have a quotient, its derivative, it's the bottom times the derivative of the top, minus the top times the derivative of the bottom. For the rest, you won't be scared. It's all over the bottom squared. This is calc, this is calc, this is calc. And then I'm going to make you promise me in the comments that you're not going to cancel those things out because that minus sign says that you can't. And then the product rule is so much fun. It's the derivative of the first times the second plus the second times the, nope, that's false, plus the first times the derivative of the second, right? Like that's the product rule. And we can do all of the things with this. We can find equations of tangent lines. We can take second derivatives. All the things that have been true for us all along are still true. Let's do a quick OYO. Let's do a quick OYO. Find the derivatives of, and we'll let this be e to the x squared plus 6x over 3x minus 5. And here we'll let g of x be, let's see, e to the x times x cubed plus 2x squared minus 3. Take a moment, hit the pause button, see what you can see. No, really, I'm going to show the answers in a moment. See, I told you I'd have this. I told you we'd get to this. Quotient rule with chain rule inside, right? This part is chain rule to find the derivative of that numerator. And then this piece is product rule, right? Right. Okay. So one more thing before we go. One more thing before we go. A population of mosquitoes is modeled by M of t, M for mosquitoes, is 120 e to the negative 0.03 t, where t is in hours. What is M prime of t? What is M prime of t? Well, M prime depends on this, doesn't it? M prime depends on this, because this 120 is just going to come along for the ride. The derivative of e to the something is e to that something times the derivative of that something, right? Like that's how this works. So this is negative 3.6 e to the negative 0.03 t. Well, what does that mean? For example, M prime of 4. M prime of 4, you substitute 4 in for this, and you get negative 3.6 e to the negative 0.12. About how big is that? That's about negative 3.193. What? Negative 3.193 what? Well, this is a prime, so it's a derivative. It's the rate of change for this thing. M is measured in mosquitoes. T is measured in hours. This is measured in mosquitoes per hour. What does that mean? It means that at the moment when you look at your clock and 4 hours have passed, which is how long it feels like this video has gone on, if you look at the clock and you see that exactly 4 hours has passed, the population of mosquitoes is decreasing at 3.193 mosquitoes per hour. That's what that means. That's what that means. So we know how to take derivatives. All the things we know from before are still in play. We know how to interpret things in context, and those are all very important. I'll see you when we gather.